Heavy rainfall on seasonal snow cover can result in much greater runoff than from rain or snowmelt alone, leading to devastating floods. This phenomenon is known as rain on snow, and it has caused some of the most destructive and costly floods in the United States, including the 1996 Midwest floods and the 2017 flood that damaged California's Oroville Dam. Many people believe that rainfall itself can melt snow, but it is actually the warm temperatures, strong winds, and high humidity that predominantly drive snowmelt during rain-on-snow events. As the rain falls on the snowpack, the water can travel relatively quickly through the snowpack's layers to reach the underlying soil. How streams respond to this runoff depends on how much water is already flowing and how saturated the soil is. If the soil is not yet saturated, it can absorb or delay a flood response by soaking up rain and melting snow. But when the ground is saturated, snowmelt combined with rain can lead to fast and devastating flooding. Forecasting whether a flood will occur requires knowledge of weather and hydrological conditions, such as soil moisture and snowpack conditions before the storm, the elevation at which rain transitions to snow, the rainfall rate, the wind speed, air temperature, and humidity, and estimates of how those factors contribute to snowmelt. Additionally, each factor varies in time during a storm and varies in complex ways, especially across a mountainous landscape. Rain-on-snow floods are characterized as compound extreme events and are hard to predict, despite the extensive damage they can cause. The middle elevations of mountains are the most susceptible to rain-on-snow events because they can experience substantial rainfall or snowfall, causing both melting and risk of roof collapses. The lower elevations primarily see rainfall, while the highest elevations have colder temperatures, promoting the continued accumulation of deep snowpack and reducing the likelihood of rainfall. The snow zone elevation varies during an event and substantially from one storm to the next, making it challenging to predict flood risk. The most destructive rain-on-snow events occur when rivers are already running high, and soils are saturated, which can occur in response to a series of warm atmospheric rivers interacting with a deep snowpack. The order in which these storms occur, or the storm sequencing, is especially important for assessing flood risk because these events are caused by rapid shifts between cold periods of snow accumulation followed by warm rainfall events. As the planet warms, there will be less risk of rain falling on snow in lower elevations as the snowpack declines, particularly in warmer regions such as the Pacific Northwest. However, at higher elevations, more frequent rain-on-snow events are expected. While warmer temperatures are expected to increase rainfall intensity, research shows that this is not the most critical driver of this risk. Much of the expected increase in rain-on-snow flood risk is a result of the rain-snow transition zone expanding higher in elevation to include alpine areas that historically received predominantly snowfall. Flood control and reservoir management systems in mountainous regions must consider these future changes in rain-on-snow events to understand and prepare for the local flood risk as the planet warms. The response of rain-on-snow flood risk is expected to change in complex and often contradictory ways in a future climate, and the projected changes are likely to vary by region, season, climate model, emission scenario, and future time horizon. More research is needed to fully understand this costly risk.